Let's go ahead and examine sig figs. If anything students really hate about Gen Chem, it's probably sig figs and their rules. They're hard to remember, students don't understand the point behind them, but bottom line, they're vital and they can be the make or break between your grade and a grade lower. So you need to get your sig figs down, understand, how to use them properly, how to recognize them, what are the rules, and how do you apply them when doing addition, subtraction, or multiplication, division within your calculations. Previous module, we already talked about the importance of sig figs. So if you're not sure of the importance, go ahead and watch module 1B again and, come see me if you need help. But I go through the questions in there, but you should really understand why we're doing them. In this module, we're going to focus on how to recognize them. So first, we need to cover the rules. The rules of sig figs are as follows. All non-zero digits are significant. Students have an easy time with that. If it's not a zero, it is significant. So 5.32 has 1, 2, 3 sig figs. 2332, 1, 2, 3, 4 sig figs. Again, most students don't struggle with that. It's the zeros that are going to throw students off. But again, you need to know whether it's significant or not. If you have a zero that is between other sig figs, it is significant. So what I mean by that is like a sandwiched zero. It is sandwiched between two other sig figs or significant numbers. 5.02, 1, 2, 3 sig figs. That zero in the middle is significant. 5.002, 1, 2, 3, 4. That has 4 sig figs. Both zeros are significant. Even though they're right next to each other, they are both in fact significant. Now, one that really throws students off is leading zeros and trailing zeros. Leading zeros are not significant. So 0.000532 only has 1, 2, 3 sig figs. One way to remember it for some students, not all, but some students it helps, is if I put this into scientific notation, those zeros would no longer be there. If I put this number into scientific notation, it would be 5.32 times 10 to the minus 4, 1, 2, 3 sig figs. So if you're unsure on the leading zeros, try putting it into scientific notation, and hopefully that will help. 0.000502, 1, 2, 3, 4 sig figs. The zeros in between the 5 and the 2 are between significant numbers, so those are significant. But the leading zeros are not significant. Again, if you are unsure, put it into scientific notation, 5.002 times 10 to the negative 4. I have 1, 2, 3, 4 sig figs. So students have a kind of hard time with leading zeros. Students have a very difficult time with what we call trailing zeros. A trailing zero is a zero at the end of a number. And it truly depends on if there's a decimal point and where the decimal point is, if the number is significant, if that zero is significant or not. Final zeros, some people call these trailing zeros because they trail the number, with a decimal point are significant. So saying 5.00, this has 3 sig figs. The trick here is the zeros follow an integer and have a decimal place. The zeros on this 5.00 are following an integer. Remember, integer is your whole numbers, but not 0. So 5.00 has 3 sig figs. If I say something is 5.00, I mean specifically 5.00. I don't mean 545, 5.45, or 4.97. I mean 5.00. If I have 0.05020, that has 1, 2, 3, 4 sig figs. Again, this one's going to confuse students because of the leading zeros. If I put that into scientific notation, 5.020 times 10 to the second. This trailing zero is significant because it is following an integer and a decimal place. So it has to have a decimal place before or after it. It can be before it, it can be after it. We've seen both examples here. Here the decimal is before. Sorry, I know you guys can't read that writing. Here, let's go through this. The decimal here is before the zeros. The decimal here, the decimal is before zeros. Let's call that what it says on the slide. I forgot about that. Sorry. It's before final zeros. Okay, so that is 4 sig figs. Now 150 with a decimal place, this has 1, 2, 3 sig figs. This one has a decimal after. But that 0 is still following an integer, and there is a decimal place here after. So therefore, it is still a significant figure. That 0 is significant. I think about it like, kind of like the decimal place is holding that 0 in place. Now, final zeros in a number with no decimal point are ambiguous, meaning that they are not significant. So if I look here at 150, just saying 150 with no decimal place, this has 2 sig figs. 2000 with no decimal place just has 1 sig fig. You're going to see this in other classes, and they're going to tell you it doesn't matter, just take a certain number, etc. I'm not lying to you, though, when I tell you these are actually the rules of sig figs. You can look on the internet, and this is the rules that we're going to give you. Students just have a hard time with it, so a lot of subject matters aren't as particular as we are in chemistry. But again, in chemistry, we are very particular. We need your sig figs to be correct. So, hard things for students is captive zeros, 0, 0 sandwiched between two things. Those students can recognize pretty easily are significant. But your leading zeros are not significant. Trailing zeros, it depends on if there is a decimal place and where that 0 is in comparison to that decimal place. If it is a 0 after an integer with a decimal place anywhere in the number, it will be significant, even if that decimal place comes after the 0, such as in the 150 with a decimal place on the end. That still has 3 sig figs. Sometimes scientific notation is required. What if I wanted to express 1500 to 2 sig fig? To 3 sig figs. This is currently showing 2 sig figs, right? What if I wanted 3 sig figs? I would have to put this into scientific notation. 1.50 times 10 to the third. Now, why would I do that? It depends on the measurement. Depending on what calculations I'm doing, I may end up with an answer that is like 1500, but because of my calculations, I actually need 3 sig figs. So in that case, I would be required to do scientific notation. Personally, I only require scientific notation if it's required by the question to get your correct sig figs. Otherwise, I don't care if students leave it in scientific notation or regular integers, but some faculty will prefer a different method. What about 9,000? This again, 9,000 only has 1 sig fig. What if I want 2 sig figs? I would have to write 9.0 times 10 to the third. Writing 1.50 times 10 to the third, or 9.0 times 10 to the third, that is giving me the correct number of sig figs. 1.50 times 10 to the third is 3 sig figs. But it's still telling me 1500 if I take it out of scientific notation, so it's still the correct value. Writing 9.0 times 10 to the third, that still represents the value of 9,000, but it is giving me 2 sig figs. What happens when you have to round? Students are very stressed out about rounding. And we follow the general consensus that if the number that the leftmost digit to be removed is greater than or equal to 5, you're going to round up. If the leftmost digit to be removed is less than 5, you're going to round down. So there may be different rounding conventions on a class you've had before. In this class, this is the method we follow. Let's round each number to 3 sig figs. I want 1, 2, 3 sig figs. I need to cut the number right here. The leftmost digit to be removed is a 7, so I'm going to round up. My final answer will be 3.56. 5.52, here's my 3 sig figs. My leftmost digit is a 2. I am going to round down. And I have 5.52. 3.555, 1, 2, 3 sig figs. I'm going to cut my number right here. My leftmost digit to be removed is a 5, so I'm going to round up to 3.56. It's hard to see it in there, but there is a decimal place right there. 9.23499. 1, 2, 3. The leftmost digit is a 4. I'm going to round down. I will often have students ask me, but there's a 9 after the 4. What do I do? I know there's a 9 after the 4. We are ignoring any number past the first digit to be removed. If the first digit to be removed is a 5 or higher, we are going to round up. If the first digit to be removed is 4 or under, we are rounding down. It is a 4. We don't care about the 9. We are rounding down. 9.23. And 1995. 1, 2, 3. I need to cut the number here. I need to round up. When I round up, that results in 2000, which only has one sig fig. So I'm going to have to present this as 2.00 times 10 to the third, 1, 2, 3 sig figs, and I round it up. What about calculations? This is where students really kind of get confused on it and bothered by it. They have a hard time with the calculations. Addition subtraction has a different set of rules than multiplication division. You've got to get these rules straight in your head because it's the only way to do it. When you are doing addition subtraction, this is the rule students forget the most. You are asking yourself, how precise is each measurement? The answer has the same number of decimal places as the least precise measurement used in the calculation. Now, I want to emphasize something here. When I say decimal places, students very much think, well, that means how many spots in am I precise to? It really means how many places. Because if I wrote something like 1990, that is precise to the tens place. If I wrote 1990.1, this is precise to the tenths place. So decimal places isn't maybe the best word because what we mean by it and what students take by it are two different things. We mean how precise is your measurement. Are you precise to the ones place, the tens place, the hundreds, the thousands? Are you precise to the 10th place, which is the first decimal place? Are you precise to the second decimal place, a third decimal place? How precise is your measurement? You cannot make your final answer more precise than your least precise measurement. So we've got 29.52 plus 3.001 plus 7219.5. Now, when you're first learning to do this, what most students will do is they're going to line up their numbers. They're going to say 29.52, line up their decimals, 3.001, and 7219.5. They are then going to draw a line where their least precise measurement ended. When you add this up, you get 7252.021. My least precise number was 7,219.5. Therefore, I had to stop my number at the first decimal place. And I can see that pretty clearly because I've drawn on the slide, right? I've drawn where the number would end. So my final answer here would be 7252.0. What I'm going to do through most of our calculations is not do it that way because, to be honest, it's just time consuming to me. I don't like rewriting it. I recommend doing it this way until you remember the rules. And key note here, because I want to make sure to emphasize this, do not forget the 0. That 0 is that 0 is your uncertainty in your measurement. And it has to be included. Or your last sig fig. The other way to do this that I personally find to be a little bit easier, but again, do it this way until you get the hang of it, is I go through and I underline where my least precise measurement is. I see this is precise to the hundredths place. This is precise to the thousandths place. This is precise to the tenths place. When I add this up, and get 7252.021, I know that tenth is the least precise, so my final answer can only be precise to the tens place. So tenth has 1, and I get the same answer. But again, find a way to remember this rule. Do it however makes the most sense to you, but you need to practice this because this is what students are going to mess up. It is important to note that when you add or subtract, it is possible to end with more sig figs or less sig figs than you started with. For example, the example we just did, 29.52 actually had 4 sig figs. 3.001 had 4 sig figs, where 7219.5 had 5 sig figs. My final answer has 5 sig figs. So you will often see something end with more or less sig figs than it began with. This next question here emphasizes this a little bit more. I have a beaker that contained a volatile liquid. Volatile just means that it easily escapes into the vapor phase. I have a beaker containing a volatile liquid, and it was determined to have a mass of 25.57 grams. So again, if you have to, draw a picture. It'd be better than that one. It's a really bad picture. You've got this beaker here. It's not getting any better. And the beaker plus this liquid weighs 25.57 grams. 15 minutes passes, and the same beaker now has a little bit less liquid in it, and you weigh it again, and you find it to be 25.49 grams. So the mass has decreased, okay? That's because, again, the compound is volatile, and volatile means it easily escapes into the vapor phase. But it's asking me what mass of liquid evaporated. Most students can get that question correct because they just plug it in their calculator and don't think much about the answer. But what if instead of asking you what mass of liquid evaporated, I asked you how many sig figs does your final answer have? Students are going to mess that up. If you have 25.57 grams minus 25.49 grams, my final answer is 0.08 grams. First, I do not want to write, it would not be appropriate to write 0.08000 grams. We're going to see why students would mess that up when we do the multiplication division rules. But in addition to that, if I asked you the number of sig figs, this had 4 sig figs, this had 4 sig figs, this one only has 1 sig fig. So my final answer only has 1 sig fig. Again, further emphasizing that I can end with greater or less number of sig figs by the 2 examples here than I started with. What about on numbers in scientific notation? You have a few options here. You can leave it in scientific notation, you can take it out, or you can try to match the exponents. I truly don't care which way you do it. I'm going to show you what I consider to be the hard way, which is taking it out of scientific notation or matching the exponents, and then I'm going to show you an easier way. The easier way is a little complex until you get the pattern down. Once you get it down, though, it makes it a lot easier to do. It's a lot faster to do. I can check students' work very, very quickly by doing the shorthand method. Let's do it the hard way first. I have 9.2678 times 10 to the negative 4 plus 8.0 times 10 to the negative 5. So both of these numbers, I'm basically got this number and this number. They're both in scientific notation. I need to add them together. When I plug this into my calculator gives me an answer of, 1.00678 times 10 to the minus third. That is my calculated answer. That does not have the correct number of sig figs. I'll tell you that right now, okay? So how do I do this to get the right number of sig figs? Because I don't want to lose easy points. Sig figs, relatively speaking, are easy points once you know the rules. I'd rather you get these down so that you can focus on the hard stuff and not lose points on the things, not get a perfect score because you didn't know your sig fig rules. 2 ways we can do the hard way. Take it out of scientific notation or match the exponent. Let's take it out of scientific notation first. 9.2678 times 10 to the negative 4 is 0.00092678. 8.0 times 10 to the negative 5 is 0.000080. Draw that in to emphasize where my number is going to stop. Add it up. I get 0.001, 0.00678. I can tell now that my number is going to stop at the 6th decimal place. So I need to round. The first number being dropped is a 7. I'm going to round up. So I can say 0.001007, or matching to my calculator, I can say 1.007 times 10 to the minus third. Absolutely correct. And you are welcome to do that if you would like. That is totally fine. Another way we can do this, though, is by matching the exponents. So we can either put everything into the 10 to the negative 5 or everything into 10 to the negative 4. I'm going to put in 10 to the negative 4 just because I already have it written out and I don't have to recalculate while I'm making a video. 9.2678 times 10 to the negative 4. And if I put 8.0 times 10 to the negative 5 into negative 4, that would be 0.80 times 10 to the negative 4. Following the same process, when I add these up, I see I get 10.0678 times 10 to the negative 4. Round that to 10.07, 10 to the negative 4. But by scientific notation convention, we wouldn't leave it like that. We would write 1.007 times 10 to the minus 3. Okay, so those are the two harder ways to solve it. Doable, but harder, especially if you're in a hurry. The easier way is to look at the number itself and determine where your decimal places lie. So if I have 9.2678 times 10 to the minus 4, this minus 4 here is telling me the decimal position of the 9 here, right? If I took that out of scientific notation, 0.000092678, 1, 2, 3, 10 to the negative 4. It's telling me that 9 is at the 10 to the negative 4th position. Well, if that's at the negative 4 position, then my 2 has to be at the negative 5. My 6 has to be at the negative 6. My 7 has to be at the 10 to the negative 7. And my 8 has to be at 10 to the negative 8. I realize this is really messy on this slide, so I'm going to try to write this back over here. This is 10 to the negative 4. This is 10 to the negative 5. 10 to the negative 6, 10 to the negative 7, 10 to the negative 8. Again, I know this because the negative 4 here is describing the position of that very first number. If I do the same thing to 8.0 times 10 to the negative 5, this negative 5 is describing where the 8 is, which means this 0 has to be at the 10 to the negative 6 position. So 10 to the negative 5, 10 to the negative 6. Now when I add these together and I get 1.00678 times 10 to the minus third, that means this is 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8. But I look at my numbers, I look at my two possibilities. One number is precise to the 10 to the minus 8 position. One number is precise to the 10 to the minus 6 position. That means my final answer can only be precise to the 10 to the minus 6 position. Anything past that has to be rounded. So I've got 1.00678. I'm going to cut the number right here, times 10 to the negative third, which gives me 1.007 times 10 to the negative third, which again matches everything I've seen in all the other ways I have done this question. And I know that's a little hard to do, but your final value here can only be precise to the least precise measurement, which is 10 to the negative 6 position. Because the negative 8.0 times 10 negative 5 is only precise to the 10 negative 6 position, while 9.2678 times 10 negative 4 is precise to the negative 8 position. Let's do a couple more and see if we can figure this out. I am going to try to minimize this a little bit to clean up some space, just because I know it's kind of messy. go ahead and look at this example here. 4.5972 times 10 negative 9 plus 1.2379 times 10 negative 7. The negative 9 here is telling me the position of the 4. So I know this is 10 to the negative 9, which means the 5 is 10 to the negative 10. The 9 is 10 to the negative 11. The 7 is 10 to the negative 12. And the 2 is 10 to the negative 13. The 7 here is telling me the position of the 1. So 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, 10 to the negative 10, and 10 to the negative 11. I look at the two numbers, and I'm going to compare 10 to the negative 13 and 10 to the negative 11. Which one is least precise? 10 to the negative 11 is less precise, so my final answer can only be recorded to the 10 to the negative 11 position. Now when I add these up, I get a number of 1.283872 times 10 to the negative 7. 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, 10 to the negative 10, 10 to the negative 11. Here's my precision. So I need to cut my number at that position. Between that 8 and 7. My final answer here, 1.283, and I'm going to round up 9, because I'm dropping a 7, times 10 to the minus 7. I'm then going to check my answer. Negative 7, negative 8, negative 9, negative 10, negative 11. I have the correct answer. My final answer, move this so you can actually see it. Oops, wrong button, 1 second. I apologize. My final answer is precise. To 10 to the negative 11 position. What if I do this problem here? Now these numbers are actually positive, so I gotta count a little bit, I gotta think about how I'm counting, right? This one may be easier to take out of scientific notation because the numbers are relatively small. But I'm gonna do it in scientific notation and then show it to you out, so showing you that it does work either direction. If I have 2.45 times 10 to the second, that means this is at my 10 to the second position, this is my 10 to the first position, and this is 10 to the 0 position. 10 to the second means your hundreds place, 10 to the first means your tens place, and 10 to the 0 means your ones place. 2.34 times 10 to the third, 10 to the third, and 10 to the third, let me write that down here, 10 to the third, if you cube 10, that gives you your thousands place, right? So if you take 10 squared, it gives you 100, 10 raised to the first power of 10, 10 raised to 0 is your ones position, 10 to the third is your thousand. So this is precise to the 10 to the third, 10 to the second, and 10 to the first. Now when I put this in my calculator, it's going to give me just a flat answer. It's going to say 2585. This is my 10 to the 0 position, 10 to the 1, 10 to the 2, and 10 to the 3. This is valid to 10 to the 0 position, whereas this is only valid to 10 to the 1. 10 to the first power is less precise than 10 to the 0. So you have to think about which way you're counting. If you're counting in positive numbers, you got to pick the bigger number. If you're going in negative numbers, you got to pick the smaller number, right? Because 10 to the negative 6 is a bigger number than 10 to the negative 8. So you got to think about which direction you're going here. My answer can only be precise to the 10 to the first position, so I have to round to this position. I'm going to drop that 5 and round this to 2590, and that would be my final answer. I could also report this, some students have asked, yes, you can report this as 2.59 times 10 to the third. Either one is correct, it's still precise to the tens place, because this would be 10 to the third, 10 to the second, 10 to the first, and my final answer is precise to the 10 to the first position. But this question may actually be easier to do out of scientific notation, but I wanted you to see you could do either way. 2.45 times 10 to the second is 245. 2.34 times 10 to the third is 2,340. When I add those up together, I get 2585. But I see this is only precise to my tens place, so I'm going to round to 2590, or again, 2.59 times 10 to the third. If you don't want to do your scientific notation sig figs that way, you don't have to. But if you can get the pattern down, it can actually make this whole thing a lot easier for you. So I recommend trying to get it figured out. Multiplication division asks you how many sig figs are there. You're going to find the number with the least number of sig figs, and that's how many sig figs your final answer will have. This is the rules that students tend to prefer. For example, 2.99 times 7.3. 2.99 has 1, 2, 3 sig figs. 7.3 has 1, 2, 2 sig figs. When I put this in a calculator, I'm going to get a calculated value of 21.827. But 2 sig figs is my least number of sig figs. I'm going to keep this to 2 sig figs. 1, 2. I'm dropping that 8. I'm going to round this up to 22. I need 2 sig figs in my final answer. So I'm going to round this to the value of 22. 2.93 times 4.2 times 10 to the second. I know it's hard to read it like this, but this is like 1 unit. This is like 1 unit, okay? This has 1, 2, 3 sig figs. This has 1, 2 sig figs. When I multiply these together, I get a calculated value of 1230.6. 3 sig figs, 2 sig figs. 2 is a smaller number, 1 and 2. I need to cut my number right here, so I'm going to round this to 1200, or as some students prefer, 1.2 times 10 to the third. Either one of those would be valid, but they both have 2 sig figs. Now, when you're doing calculations with multiple steps, you may have to do this calculation twice, and that's what I recommend, to be honest with you, doing the calculation twice. You do it once, just straight through in your calculator to get a calculated value. So for example, 12.3 divided by 8.72 plus 295.7. I plug that in my calculator and I get a calculated answer of 297.1105505. But now I'm going to do it a second time to determine my sig figs, and I have to determine sig figs at each step within the calculation. Every time I change rules, I have to determine the new set of sig fig rules I'm going to follow. We are following order of operation here, so when I have 12.3 divided by 8.72, and then spaced from that is plus 295.7, that means I'm doing this one first. This is number 2. 12.3 divided by 8.72, I look, this has 3 sig figs. This has 3 sig figs. And when I actually do that math, I get a value of 1.41. 3 sig figs, that's perfect. Now I'm going to add this to 295.7. This is precise to my hundreds place. This is only precise to my tens place. My final answer can only be precise to my tens place. So my final answer will be 297.1. So again, you're having to do the calculation for sig figs. You're having to go through the calculation step by step by step to see where your sig figs are at each step in the reaction or in the calculation. If I have 12.3 plus 897.21 divided by 67.982. Now, by orders of operation, when I have the plus up here above a division bar like this is implying there's parentheses here. I don't have to put parentheses there. It's implied by the way it's written. 12.3 plus 897.21 gives me a calculated value of 909.51. But 12.3 is precise to my ones place, or my tenths place, while 897.21 is precise to my hundreds place, which means my sig figs are actually stopping here at the 5. I'm going to highlight it and underline it. I'm not going to round yet. I'm going to show you the last example on the slide has round off error to it, so we don't want to round too soon. I want to carry 1 or 2 extra digits until the end and then round at the end. But I want to mark where my sig figs are, because now I'm going to do division. 67.982. Here I have 1, 2, 3, 4 sig figs. 1, 2, 3, 4, 5 sig figs. When I calculate this out, I get an answer of 13.3786 885. But my least number of sig figs is 4. 1, 2, 3, 4. I need to round my number here. And I'm going to round this to 13.38. Because I'm dropping an 8, I'm going to round up. Now, next one. 9.972 times 10 to the negative 9 plus 5.80 times 10 to the negative 11 divided by 4.8 times 10 to the negative 8. First thing I have to do is the addition. When I add these together, I get the numerator, I get a numerical value of 1.003 times 10 to the negative 8. This is still divided by 4.8 times 10 to the negative 8. But I have to check my sig figs. Negative 9, 10 to the negative 10, 10 to the negative 11, 10 to the negative 12. Negative 11, 10 to the negative 12, 10 to the negative 13. So I need my answer to be precise to the 10 to the negative 12th position. I've got negative 8, so 10 to the negative 8, 10 to the negative 9, 10 to the negative 10, 10 to the negative 11. I need this precise to the negative 12th position. I need to add a 0 because that is what's giving me the 10 to the negative 12th position. So now what I'm actually calculating is 1.0030 times 10 to the negative 8 for my precision, divided by 4.8 times 10 to the negative 8. Now, the numerator has 5 sig figs, the denominator has 2 sig figs. In the end, it wouldn't have mattered if I hadn't realized the 0 was missing, because it's going to cancel out anyway. I'm going to calculate an answer here, 0.2089583333, which I am going to round to 2 sig figs because of the denominator being 2 sig figs. Overall, 0.21 will be my value. However, that 0 in the numerator is important if I'm watching your work, right? If I'm watching you do your calculations, watching your work, or if you had an example that wasn't divided by a fewer number of sig figs, that 0 would have been vital for the calculation. And the last example for this module, 31.49 minus 12 times 434.049 minus 432.1. This question is intentionally designed to emphasize round-off error. So, if I take 31.49 and subtract 12, I get 19.49. This is precise to the hundredths place, this is precise to the ones place. My number here, my sig figs are here at 19. 434.049 minus 432.1 gives me a value of 1.949. Precise to the thousandths place, precise to the tenths place, precise to the tenths place. If I was to round, I'm going to do this over here. If I was to round these, I would say 19 times 1.9, because I'm going to drop a 4 and a 4, right? I'm not going to round up there. That 9, I don't care about the 9. I drop that very first digit to be dropped is what I'm looking at. I'm going to round to 19 and 1.9. If I take 19 and multiply that by 1.9, I get a value of 36. But if I don't round and I do the calculation full out and carry that extra digit until the end, my calculated answer here is 37.98601. This is precise to my ones place. This is precise to my tens place. My final answer can only be precise to my ones place, because the one position is less precise than the tenths place. Overall, I'm going to round. I'm going to cut the number here and round. I'm going to get a value of 38. And 38 and 36 may not sound drastically different. However, I guarantee you, if I give you an assignment and you score a 38 out of 40, you're going to want that score in the grade book instead of a 36 out of 40. So the issue here is your value has round-off error. We minimize that round-off error by not rounding until the end of the calculation, but instead marking where our sig figs are. Now, I don't want to be extreme about that. I'm not saying that, like, up here where I had 13.3786885, I would carry all those numbers. I would carry 13.378, maybe 86. 1 or 2 numbers past where you know your sig figs are will minimize your round-off error. But be careful and don't round too early.